Hello again. So now we are going to talk about rational functions, and we're dealing with two parts. We're going to deal with the part one first. We're going to talk about the form. We're going to talk about the characteristics of rational functions, and then we're going to hopefully talk about graphing and specifics of that. Okay, standard form. Any rational function that's going to show up is going to in a form of f of x equal to px over qx. I wrote it up right here for you guys, where p of x and q of x, they are polynomial functions, and it is very important that the denominator q of x is not equal to 0, because you cannot have a 0 in a denominator in a rational function, just like a rational number or rational expressions. You cannot have a denominator of 0. All right, now there are four possible different graphs that you're going to get depending on what these two polynomial functions are. And we're going to deal with the first two. All right, the first case, we have this function, and f of x equal to 4x over x squared plus 1. And if you look at the characteristics of it, let's look at the asymptotes, because that is the most important part of any rational function. So let's see what happens. For vertical asymptotes, you're looking at the denominator. So x squared plus 1, you set that equal to 0. You notice that this equation doesn't have any solution, right? It's x squared plus 1. You cannot factor it. It doesn't have any solution. So this does not have any vertical asymptote. And also, if you look at the horizontal asymptote, also it doesn't have a horizontal asymptote. Everything will work in here. Now, in case you don't know how to graph this, we're going to use table of values. There is no easier way to do this except using Desmos or the graphing technology. But if you want to take our time, it will end up being using a table of values, which is tedious. But let's go through a few points and then we plot using Desmos. Okay, so now if you create a table of values, I went through, found or chose x values being -4, -2, -1, -0.5, 0, 1, 2, 4. I chose these ones. You can choose whatever you want, as long as they're symmetric based on the origin. So some values to the left, some values to the right of the origin, and then plot them in and plug it back into the equation first, and then you get the coordinates, and then you have to go graph. All right, to do that, we're going to go and use Desmos. So let's go to Desmos and do that, and then come back. Okay, so now we're going to go to Desmos. Here it is. I typed in the function and also typed in the table of values. I am not going to do the table of values after this example anymore. It's just tedious, but you guys can do that on your own. But I just want to show you that that's what you have to do. So the table of values, I basically chose these random numbers, values for x, plug it back into the equation, did the math, and then come up with the values for y. Now look what happens when we graph, we plot them. Here are the graphs, okay, and you can see the graphs, the points, the coordinates in there. They're approximate, not exact, and that is basically the pattern. The part that you don't see is the 0, 0. So let me go back. I purposely didn't put 0, 0 in there, but let's put 0 and 0. Excellent. All right, now let's look at what happens. We actually, when we click the graph to graph, here it is. All right, and then you can see that it's being, the graph doesn't have a vertical asymptote, because the denominator can never be, you cannot find the non-permissible values for any values of x. X squared in here, x squared plus 1 can never be 0. And but it turns out that this graph is very unique. It does have maximum minimum, but you don't need to worry about that until calculus. But other than that, that's the graph. And yeah, it is interesting, because if I zoom in, you notice that, or zoom out, whatever you can notice, that both graph, they actually won't cross the x-axis. on the left and on the right. Very, very unique behavior for this graph. And it turns out that whenever you have a setup like this where the numerator has a different has a lesser degree polynomial than a denominator, it may give you a situation like this. But it has to do with the denominator as well. If the polynomial of the in the denominator is non-factorable, or that doesn't have any vertical asymptotes, so that makes a difference. All right, now let's go and talk about the second case. So that's the first case. Let's talk about the second case now. Okay, so this is case 2, but before we go to case 2, I just want to make sure that horizontal asymptote, for the first part we didn't have it either, so we don't have neither horizontal or vertical asymptote for the first part. Now here is the second. The function does have a vertical and a horizontal asymptote. So here it is. Let's go through it. For vertical asymptote, we really simply let's do the vertical asymptote, VAS. Okay, so basically you have to set the denominator equal to 0, and you will get the two vertical asymptotes. All right, so these are the equation of the vertical asymptotes: x equals 2 and x equals to x equals to 1, x equals to -1. Now the horizontal asymptote is, this is the pattern that it was found with any polynomial, with any rational function where the polynomial in the numerator, the degree of that is equal to the degree of the polynomial in the numerator. So whenever you have a setup like that, you could end up getting a horizontal asymptote, and this is the way you do it. You have to divide all terms in both numerator and denominator by the highest degree term of the numerator. Okay? So basically what you will do is that you will just do the division x squared divided by x squared on top, and then you do the same thing for all of these, and the only catch to that is that you have to -1 and then divide that by x squared. But here's the thing, we are assuming that x is a very large number because we can choose that, and if that's the case, then 1 over x squared, this will be very close to 0. This would be actually very close to 0. It will be non-existent. All right, so now the final value basically will be x squared over x squared, that's 1. X squared over x squared is 1, so this would be equal to 1. So that means that y equals to 1, that is your horizontal asymptote. Okay, and that's how you always calculate the horizontal asymptotes, with the rational function that looks like this, where the degree of the numerator is equal to the degree of the denominator. Let's go ahead and graph it using Desmos. Okay, so this is the function I typed in. Okay, and basically let's look at what's going to happen. Excellent. Let's compare what we have done. First of all, the asymptotes that we talked about, x equals to 1 and x equals to -1, those are the vertical asymptotes. So right here, right, and then x equals to 1 right there. Then the horizontal asymptote, so those were the vertical asymptote. The horizontal asymptote, we just did the algebraic work for that, and that would be a y equals to 1, and you notice that is a 3-piece function. This graph, in comparison to the graph that we had before, this is a discontinuous function, discontinuous graph, because there are 3 pieces. They're not attached to each other. All right, now we call them discontinuous function. All right, that's basically it. Now, if you wanted to graph this freestyle, it would have taken you a lot of time because you had to come up with a few points so that you can draw it, but you still wouldn't be able to graph this very accurately. So just be aware that in this case, technology is very useful and you should use it. All right, that is it.